Hello students, I am Dr. Shilpa K. Gowda, Department of ECE SJBIT. Today I am going to explain the operational amplifier. So that is integrated circuit operational amplifier and its applications. So this is the basic op-amp circuit. Here the input and output stages for bipolar and bi-FET operation amplifier is shown in the figure A and B. The differential amplifier input stage has two inverting and non-inverting high impedance input terminals, and the emitter follower output stage has a low impedance. An intermediate stage between the input and output stage is largely responsible for the op-amp high voltage gain. Figure A shows a BJT input stage while figure B has a FET input stage. Appropriately, op-amp that exclusively use BJT are termed bipolar op-amps, and those that use a FET input stage with BJT addition stages are referred to as bi-FET op-amps. So these are the important parameters of op-amp. Some of the most important parameters of 741 IC are listed in the data sheet shown in this figure. So first we are considering here parameters, condition, minimum, type, maximum and unit here. Large signal voltage gain, it is represented by AB, and the condition will RL will be greater than or equals to 2 kilo ohm, and V out will be equals to plus or minus 10 volts, where minimum will be 50,000, type will be 200,000. Next, input bias current, it will be IB, where the type will be 80 and maximum will be 500, unit will be nano amps. Input offset voltage V0, where the condition will be RS will be less than or equals to 10 kilo ohm, type will be 1, maximum will be 5 and unit will be millivolts. Input offset current I0 will be, type will be 20, maximum will be 200, unit will be nano amps. And input resistance Ri will be minimum 0.3, type will be 2, unit will be mega ohms. And output resistance R0 will be, type will be 75 and unit will be ohms. Here the large signal voltage gain AV is also identified as the open loop gain. For this IC741 is listed as 50,000 minimum and 200,000 typical. This means, for example, that a signal applied has a voltage difference between the two input terminals is amplified at least by a factor 50,000. The typical amplification is 200,000 and the maximum amplification can be considerably greater. This is similar to the situation with the HFE of a BJT, where the manufacturer specifies a minimum, typical and maximum values. The input bias current IB is the base current for the op-amp input stage transistors. Now the figure in the 15 is listed 80 nanoamps typical and 500 nanoamps maximum. Ideally, the input stage transistor should be perfectly matched so that zero voltage difference between the input terminals should produce a zero output voltage. In practice, there is always some difference between the base emitter voltage of the transistor, and this results in an input offset voltage that might be as large as 5 millivolts for a 741 op-amp. Similarly, because of a mismatch of input transistors, there is also an input offset current for the 741. I0 is a maximum of 200 nanoamps. The input resistance and the output resistance are the resistances at the op-amp terminals when no feedback is involved. Virtually all op-amp applications use negative feedback, so these quantities are modified in practical circuits. So the DC supply voltage for electronic circuits can vary with the supply current changes, and in some cases there is an AC ripple voltage superimposed on the DC. The supply voltage changes can be passed to the output of an amplifier. Ideally, the supply voltage variations should have no effect on the circuit output. So how good the amplifier is at attenuating supply voltage variations is defined by the power supply voltage rejection ratio. This is usually specified in decibel form. Common mode inputs are voltage changes that are applied simultaneously to both input terminal of an integrated circuit operational amplifier. common mode input voltages can be passed to the output. The common mode rejection ratio defines how good the amplifier is at attenuating common mode input voltages. Next we have biasing operational amplifiers. So biasing bipolar op-amp circuit. So like other electronic devices, operation amplifiers must be correctly biased if they are to be function properly. The inputs of an operation amplifiers are the base terminals of the transistors in a differential amplifier. Base currents must flow into these terminals for the transistors to operate. Consequently, the input terminals must be directly connected to suitable DC bias voltage sources. So the most appropriate DC voltage level for biasing bipolar op-amp inputs is approximately halfway between the plus and minus supply voltages. One of the two important input terminal is usually connected in some way to the op-amp output to facilitate negative feedback, where a positive or negative supply is used and the other input might be biased directly to ground via signal source. Base current IB flows into the op-amp non-inverting input via the signal source, while IB2 flows from the output into the inverting input as shown in the figure. And also the figure shows that a situation in which one input is connected via resistor R1 to ground and the other is connected via R2 to the op-amp output. Once again, the base current for the input stage transistors flows into both input terminals R1 and R2 should have equal resistance values so that the voltage drop IB1 R1 and IB2 R2 are approximately equal. Any difference in these two voltages drops appears as an op-amp DC input voltage which may be amplified to produce a DC offset at the output. If very small resistance values are selected for R1 and R2 in the circuit, then a very small input resistance would be offered to a capacitor coupled signal source. On the other hand, if R1 and R2 are very large, the voltage drop IB1 R1 and IB2 R2 might be large. An acceptable maximum voltage drop across these resistors must be very much smaller than the typical VBE level for a forward bias emitter junction. That is, VR1 equals to VBE by 10. Next, the above figure shows a voltage divider R1 and R2 providing an input terminal bias level from the supply voltages. The voltage divider current I2 should be selected to be very much larger than the input bias current. This is to ensure that IB has a negligible is selected as I2 minimum than the bias current. This is to ensure that IB has a negligible is selected as I2 minimum will be 100 IB maximum. Then R1 and R2 are simply calculated as VR1 by I2 and VR2 by I2 respectively. Resistors R3 in the figure should be selected approximately equal to R1 parallel to R2 to minimize any difference between IB1 into R1 parallel to R2 and IB1 R3 that could behave as a DC input voltage. So this we have considered the problem here. Next, voltage follower circuit. This is a direct coupled voltage follower circuit. So in this here, IC op-amp can be used for various applications. One of the simpler application is direct coupled voltage follower circuit. Output terminal is connected directly to input terminal. The input signal is applied at non-inverting terminal, and the figure shows B shows that basic op-amp circuit connected as a voltage follower. Because of a differential input stage V2, which is same as V0, must be equal to Vi. When V2 is higher or lower than Vi, the voltage difference V2 minus Vi helps to maintain the equality within input. When V0 is slightly greater than Vi, then Q2, that is pin number 6 base voltage, is higher than Q1 pin base voltage. Thus, IC2 is increased and causes increase in voltage drop across RC, reducing VB3. This causes the output voltage back to equality with the input voltage. Similarly, when V0 is lower than Vi, base voltage Q2 is lesser than the base voltage Q1. Reduces the IC2 in turn reduces voltage across RC, causing increase in VB3 and drives V0 back to equality with Vi. Next, when the input voltage is increased or decreased, feedback effects causes the output to follow the input. The difference between output and input voltage can be calculated from the output voltage level and the op-amp open loop voltage gain. So voltage follower, therefore voltage follower has high input impedance, low output impedance and voltage gain of 1. Next, this is a capacitor coupled voltage follower circuit. So here when a voltage follower is to have a capacitor coupled input and output terminals, the non-inverting input must be grounded by a resistor. The resistor is required for passing bias current to the non-inverting input terminal. It also offers an input resistance to the signal source rather than a short circuit. Because the load is capacitor coupled, the DC output offset voltage might seem to be unimportant. However, the DC offset voltage at the op-amp output terminal can limit the amplitude of the output voltage. So, a resistor R2 equal to R1 should be included in series with the inverting input terminal to equalize the IB-RB voltage drop and thus minimize the output voltage. So, the design of capacitor coupled circuit is shown in the figure here, which involves calculations of R1, C1 and C2. The circuit input impedance R1 should parallel with Z1. However, Zi is always much larger than R1, so the circuit input impedance is simply taken as Zin equals R1. Normally, the load resistance R1 is much smaller than R1 and consequently the smallest capacitor values are calculated when C2 is selected to set F1. Therefore, XC2 is equal to Z0 plus R1 at F1. Capacitor C1 should then be calculated from XC1 equals Zin plus RS divided by 10 at F1 so that it has no significant effect on the circuit lower cutoff frequency. Thank you.